Hi, I'm Kaylin, and this is my Lab 6 Magnetic Molasses Lab Report. So for this experiment, the main goal was to investigate how falling bar magnet induces current in a conductive tube and how these currents alter the magnet's motion. So for the model, we treated the magnet as a magnetic dipole and the tube as stacked conducting rings to calculate induced currents and magnetic forces using Faraday's law, Biot-Savart, and Newton's laws. And then the method was to use closed grip to measure the real fall time of the magnet drop through a conductive tube. And so the main result that I got after averaging all the times that it took for the magnet to exit from the tube once it was dropped was 1 minute and 34 seconds, and the computational time was 1 minute and 11 seconds. So for some key equations and principles, we use Faraday's law, which tells us that a changing magnet's flux induces its inf, and then Ohm's law, which converts the inf into a current around each ring of tube, and then using Biot-Savart's law, we approximate the magnetic field created by those induced currents, and that induced field opposes the falling magnet, which is a direct demonstration of Lenz's law. And then finally, we use Newton's second law, which allows us to compute the magnet's acceleration as these forces act on it. And just more generally, we know that for all actions, there's an equal and opposite reaction. So for the experimental setup, the tube's measurements were 18 inches by 1.5 inches. We also used a stopwatch to calculate the amount of time that it took the magnet to exit upon dropping it into the tube. Obviously, the magnet that we used was a bar magnet, and then the system was the bar magnets and the conductive tube, and then the surroundings was the rest of the environment. And again, the average time that I calculated was 1 minute and 34 seconds. And then for the coding model, in the computational model, we wrote functions to calculate magnetic fields, induced currents, and net forces at each moment in the fall. The simulation tracks the magnet's positions and velocity over time and updates the forces accordingly. The code produced a fall time of 1.1 seconds, which is reasonably close to our physical measurement given the complexity of the system. And for the comparisons and errors, again, for the experimental time, I calculated 1 minute and 34 seconds. The computational time was 1 minute and 11 seconds. And then the difference was 23 seconds, which really isn't bad. I think it means that like my experimental time was pretty close to the expected time. And then for assumptions, we can assume that air resistance is negligible. For some errors, we can assume that maybe the friction against the tube wasn't considered in the calculation, as well as human error. Maybe when using the stopwatch, starting and stopping the stopwatch might have been a bit delayed, or maybe even a bit ahead. And so for the what if and why questions, the first being if the resistivity of the conductor were reduced to 0, what would happen? And basically, the induced current would become extremely large and produce a magnet field that completely opposes the magnet's motion. This would cause the magnet to fall very slow, almost approaching levitation-like motion. And then if there were holes or slots cut into the tube, the ring's currents wouldn't be able to form closed loops, which would significantly reduce the induced current and magnet braking, and the magnet would fall much faster, almost like free fall. And so for the conclusions and what I learned, basically a falling magnet induces currents in a conductive tube that produces a magnetic force opposing its motion, which caused a slowdown consistent of Faraday's and Lenz's law. Again, the average time that I calculated was 1.34 seconds, and the computational time was 1 minute and 11 seconds, and the difference was only 23 seconds. So yeah, that's the end of my report. Thank you so much for listening.